A very welcome to all who have joined the short-term training program. So we are about to start our second session of the short-term training program. The session in this session, our speaker is Dr. Shaptoshi Ghosh. And before we start with the second session, let me introduce Dr. Ghosh the to everyone. Dr. Ghosh has a proven record in 5G focused research and development with over 8 years of experience specializing in network softwareization, automation, and orchestration. With a background in academia, Dr. Ghosh received several national and international fellowships such as NET, GATE, Erasmus Mundus, and Marie Curie, and contributed to flagship European Union and UK funded projects like Horizon 2020, Innovate UK, EPSRC, DSIT, and DASA. He is currently associated with Digital Catapult's commercial R&D division R&D division as a 6G network orchestration technologist with London South Bank University and as a senior research fellow in the Department of Electrical and Electronics Engineering as a senior research fellow. His research interests and expertise are scoped but not limited to knowledge defined networking, cognitive net routing, and network intelligence. Dr. Ghosh is also a certified network engineer with CCNP and JNCIA. He is an active contributor to knowledge, holding two patents, publishing research articles in high impact factor journals and conferences, and a reviewer of publishers like IEEE and IET. I would request Dr. Ghosh to continue the session.
Thank you. Am I audible?
Yes, sir.
Right. Let me just quickly share my screen. Um, just a moment. Sorry for the delay. Just give me a second. I'm having some issue from my side.
Okay, fine, sir.
Am I audible?
Yes, sir.
Okay.
Yes, sir.
Yeah, just give me 1 minute. I can't share my screen from this laptop. I just rejoin in like 1 minute. Okay.
Okay, fine, sir.
Yeah. Just give me 1 minute to just rejoin from.
I would request the participants to wait for a bit till Dr. Ghosh comes back due to some technical reasons.
Right. Can you see my screen now?
Yes, sir.
Okay.
Yes, sir.
Sorry, I had an issue from my side. Apologies for that.
No
Let
problem,
me
sir.
make it full screen. Okay. So hello and thank you for inviting me. I'm really feeling privileged for getting invited and very very much thank you for my side for everybody who have contributed organizing this session. So I will start this presentation. I'm going to keep it within an hour with a goal of having like 45 minutes of presentation and then 15 minutes of Q&A session. I'm not sure about the audience, so feel free to ask me questions. This could be basics. This could be something related to research. Um, so I'm expecting all sort of questions. So this presentation is about intent-based networking. It's a new class of networking. I'm going to go through the basic understanding of where it comes from, what type of networks you're targeting into, and then we'll see where different fields like machine learning, DevOps, these fields are also coming together in networking to make network programming more optimal. So a very brief intro about myself. I work in 5G for around last 8 to 10 years. Um, so a very commonly asked question when we see researchers working in 5G, that what exactly you do in 5G. And as you can understand, if you have a basic understanding of telecommunication networks, 5G and 4G standards are very much different from their predecessors. So if you think of like 2G, 3G, the main goal was to carry data and voice than services. So from 4G, a huge change happened that we had a mobile core which is IP based, and that changed a lot of story, and that makes application manufacturers to use a 5G or a telecommunication network as a carrier for their platforms. So. Frankly speaking, anyone who works in modern telecommunication network is not necessary to be a telecom engineer, and I am not one of the telecom engineers, so I don't work in the radio side of the story. So this is something I need to first make it clear, because new generation telecommunication is not only about bandwidths, data rates, and latency. It is also a platform where we kind of provide infrastructures for application providers to run their applications. So my working domain is mainly four. I work in the DevOps side, mainly automating and orchestrating stuff, and not as an application developer, but as a network engineer. So I write applications which run in network devices. These are called net apps, and I'm going to talk about net apps in a moment. So application that runs in network devices. And my specific area of work is enterprise networking, which is primary, and secondary areas are service provider networks and data centers. I also do machine learning operations. So MLOps engineering is a domain that comes out of machine learning field, which doesn't actually deal with the algorithm development of machine learning. Rather, it uses existing algorithms and creates a pipeline. Think of a manufacturing process that data comes to one section and it gets processed, and the process data goes to another section. And each of these sections are an operation, right? So we define machine learning pipelines, and this is called ML ops. So I work with mainly API development that enables network devices to use existing data and behave intelligently. And finally, I'm a researcher by profession, so my domain of research is mainly routing and switching. And in terms of mathematical optimization, I deal with constraint optimization problems mainly to resource constrained devices and resource constrained environment. Previously, I've worked with several UK and EU projects. For example, Horizon 2020. That was my PhD funding project. Apart from them, Innovative UK, Erasmus Mundus Plus, DSTL, EPSRC, and UKRI. So currently, I am working in the last two in the list, which are EPSRC Network Plus and the UKRI DSET Phone RC reason. So a lot of acronyms. Let me first decipher them. So EPSRC is Engineering Physics Science Research Council in UK, and we work on projects which are kind of cross-platform type project. For example, this one that I'm doing now is aiming to create a 5G network fabric across UK to connect all the power system networks. So I'm not a power system guy. So there are power system engineers working. So my job is to create a fabric that seamlessly connects with existing infrastructure. And next one is this Department of Science and Technology. Phone RC stands for Future Open Network Research Challenge. And this was something given by Innovate UK 2 years back, and the project started last year. So our job is to standardize what 6G could be. So we don't know what 6G would be in the future, but we can start planning that what type of services we are aiming at. So these are the two projects I'm working now. So I think now you can have a kind of basic understanding about my working area. So while asking question, you must kind of understand that what kind of question you can answer. Anyways, so a brief about my work area, where I work and what we do. So Catapult Network is part of UK's innovation network. So UK Department of Science Technology, we kind of create research grants, and we uh, put companies will accelerators between the academia and the industry. So problem with academia is we do a lot of theoretical work, and sometimes we don't kind of evaluate how financially viable that research is. Whereas the industry people are more keen towards the viability, how sellable that idea is. So we come in the middle. So the Catapult Network, we collaborate with academia, and we kind of create partnership with industry. And our job is to get research ideas from academia and build a working prototype, a proof of concept, you can say, and then give it to a company who can actually manufacture it and make a technology from their side. There are several catapults, there are 9 of them. I work in the digital catapult, so which is mainly um, uh, targeting the digital transformation. And we have many fields of working. 9 of them are put here on the right. So we all work from quantum to data center. So these are the scope that we work. So reason project, as I mentioned, is coming from the government of UK's Future Network Challenge, and we are mainly focusing on open networks. Now, let me first clear this idea what is openness in networking. Um, in the past, when 2G, for example, came initially, there are several standards that kind of gave the initial blueprint that how this network would look like. And one is the architecture, right? How do you implement it? There are two functioning bodies that are mainly there for governing this whole idea. One is GSM, and you must kind of remember if you have lived in that era. GSM is the first standard that came in telecommunication, 2G standard, what we say now, and also 3GPP. That's a third generation partnership project. Um, this is the body who tells, for example, the mobile network operators that okay, this is the architecture. Now if you build your network, follow this architecture. Also telling the manufacturers that if you develop or manufacture a device for mobile networks, then you should follow the standards. Now, in those standards, there's certain variables which are not clearly defined. So the vendor took the liberty to make the configuration in their own way. So as a result of it, what happened that if you need to deploy a large scale architecture, then if you have a distributed component, so this component has to be from a same manufacturer, otherwise they won't sync. So this is what in networking or closed networking means you are kind of tied by the vendor. And obviously, what you can guess out of it that then you have a monopoly of business in certain cases, and there was always a demand from the manufacturers and the operators that we need openness. We need some sort of liberty that you can buy product A from vendor A and product B from vendor B, and they can sync. So this is what open networking is. And this FONRC, which is Future Open Network Research Challenge. So future stands for the next generation, which is 6G in our case. Open networking is something that is not tied by the vendor. Okay. And this was awarded last year, and this is a 2 years project. We have just finished the first plenary meeting, which is the milestone for the first year. And on the right, you can see it's a like 12 million pound project, and a lot of partners are here. So the universities and like University of Bristol is leading this project. Then King's College London, Queen's University Belfast, and then we have Digital Catapult, BT Groups, Nokia, Ericsson. So it's a combination of private sectors and public sector universities together. Right. So with that introduction, let me first, you know, list down the agenda, what is scheduled for today. So I'll first start with the trends. What is going on in networking now? So if you are planning to move into networking, what type of network you should expect? As I mentioned, I'm not sure about the audience, but if you are undergraduate student, kind of networking that you are studying in your books, and if you come to the actual domain and of research and development, you will see things are much more different than the book. So the trends I'll first go through so that we can kind of be in the same page from your idea of networking and what's going on now and how they're related. The traditional versus classical networking, what's going on now versus what used to happen in the past. Software defined networking, a new term that came a couple of years back. When I started my PhD, that was kind of a very hyped topic, I would say. Then knowledge defined networking, extension of software defined networking, and then task and intent based networking. This is the new stuff. And the main idea behind reason is to promote or to work on a new class of network we call task oriented networking. And task oriented networking is something that comes out of intent based networking. So if you're already confused by now, don't worry, I'll go through all these terms one by one. And then why we need this type of networks? Because we need to run certain services, right? And I'll mention a couple of services. One is machine learning as a service and routing as a service. So these two are the working areas that I mainly work. And there are other researchers around the world working in the same field to create a pluggable AI component. Okay, so let's say you are a mechanical engineer and you want to use machine learning in your optimization models, but you don't want to code machine learning. So you need somebody to give you those ready-made models, and you just express your intent, what you want to do, and based on that, somebody will create models for you and train your model with data samples you collected from experiments, and then give you a trained model back. Amazing, isn't it? This is exactly what this machine learning as a service. So let's start, and I'll go through one by one. So the trend in networking, if you see what used to happen in the past, what is going on now, and what is coming in the future, um, the classic networking is more of about network configuration. So um, any network engineer, the first training that they get is to configure routers and switches. So all those protocols you study in your networking books, let's say switching protocols, spanning tree protocols, VLAN trunking protocols, routing protocols, let's say EIGRP, OSPF, ISIS. So you study their mathematical model in books, but when you implement those in a real life network, then you don't need to worry about those modeling because they're already done in the codes running inside the routers and switches. Your job is to configure those networks, and normally this is done by different means. For example, SSH or HTTP. You create a session with the router, and then you send commands. Now, sometimes you can also write scripts to configure devices, but this is more of a configuration-based networking, right? And the second problem is these commands are very much operating system specific, and these operating systems are vendor specific. So a very simple example, the one I gave before, let's say I take two companies, uh, kind of giants in network. One is Cisco and one is Juniper. Now, mostly if you go to any network infrastructure in any country, um, chances are you would see at least one of them or both of them or most of them in the deployments. So Cisco uses an operating system called Cisco iOS. It's not the Apple one. It's Internet Networking Operating System, and Juniper uses something called Junos. Now they both have functionalities, for example, for implementing OSPF, a routing protocol, but the commands are different. So if you want to create a network where half of your devices are Juniper and half of your devices are Cisco, for example, there are like two companies, one using Cisco, one using Juniper, and they got merged. Now it's a challenge for the network engineer to kind of create a blend between these two, technically isolated network and kind of combine them into one. So there always was this problem of configuration and vendor specific issues, and therefore, what happened afterwards, what is going on now, is more of network automation. So network automation is an example where software technologies are used in network optimization. Um, so automation is not new. Scripting, like shell scripting, is there for ages, and there are new automation tools, for example, Ansible, Puppet, Chef, Salt. If you want to know about these tools, just Google it. There are a lot of tutorials available. So these tools are there to configure remote devices. So you define that what you want to configure and where you want to configure, and then these tools will go and remotely configure devices the way you want it. Now, if you want the same thing in networking, so your end devices are not like your host computers, rather than network devices. So routers and switches, firewalls, servers, they are the end devices, and the configuration happens somewhere centrally. And this whole idea is called software defined networking. So a software that does all the thinking job. So the brain is somewhere in a software, and the physical layer devices, they follow the orders of that software. Benefit is now this software speak in one language. So whoever programming this network doesn't know all the devices, operating system, command structures. You just learn one language, let's say Python, and you need an API to communicate with the server where this the software defined network's brain is lying. I'll name that brain in a moment. And then this brain's job is to actually think and configure devices. So from vendor specific, we are getting vendor neutral, and we are now getting something called network operating systems, which are also getting open sourced. So you don't need to pay license if you're not making money out of those licenses. Some new protocol that has arrived, for example, from SSH based communication, we are now in RESTful communication. So REST, if you have studied software engineering a bit, it's representation of state transfer. Means it's a request response type of protocol where you, let's say, use HTTP as a carrier, and the protocol is stateless. So no request depends on a previous request. Okay. And the new stuff is model driven programmability. A huge problem that was there in the previous networking concepts was, when the data comes from the device itself has their own data structure to kind of organize data. A classic example of that would be SNMP. So SNMP SNMP is Simple Network Management Protocol, the oldest telemetry protocol in networking. So what SNMP does, it uses a data structure called MIB, Management Information Base. It's a tree-like structure, and it's vendor specific. So if you want to know that among 5 routers which are there in your network, which one is most, mostly busy, or highly occupied, then you have to get their MIPS and extract that particular variable out of it, which carries a CPU utilization, for example. Now, if you have 5 different vendors, then this MIP structure is different. So you have to parse it differently. This problem is solved with something called model-driven programmability. So this model is a data model, which is written in XML-like language, and this format is called YANG. YANG stands for yet another new generation, and this is a description telling that, okay, if I want to store my data, this is how I should store the data. And anyone who follows your model will have the data formatted and stored in that format only. So from the recipient side, if you even receive a data in a different format, this model can go and parse it or rearrange your data in a way that you can understand, right? So this is what's happening now. And what we are doing in the R&D at the moment is going to come in the domestic market maybe in a couple of years from now. And this is the future, which is network intelligence. So what network intelligence means that previously we had network configuration. Now we are configuring those devices with an automation tool. The problem here is the automation tool has to be told by a human that what's the optimal solution. And as you can understand, when the network scales, the problem also scales. A lot of new free variable gets introduced in the optimization problem. A lot of new constraint gets introduced in the optimization problem. So is it not better that give this optimization to intelligent solver, not just a numerical solver, an intelligent solver which learns from its mistakes, right? So if I just draw Tom Mitchell's definition of machine learning, if your performance increases with experience, then you are learning, right? So that experience here is your data that is collected over the time, historical data, and are you learning something from it? So if you're learning something from it, means you're intelligent. So if we use such an optimizer that learns from, let's say, the past actions taken, then we are getting into a domain called network intelligence. So here what happens, we use machine learning principles, so algorithms which are kind of designed and developed in the domain of machine learning for years, and we use those algorithms to solve specific network optimization problem. Now, networking itself, the mathematical model behind networking is it comes from two theories. One is graph theory, obviously, that defines the topology of the network and an exchange of data in a distributed system. And second is queuing theory that tells you how long does it take to send data from point A to point B. So how long this thing will wait in a particular node. If you know certain conditions, then you can measure the latency. So with those basic optimization model plus machine learning algorithm, if we now start solving them based on historical data with certain learning, on top of it, then we talk about a domain called network intelligence, and this is the problem that we are trying to solve when we refer future networks. So with that, let me start, explaining the system design from the classical network to the modern networks. So traditionally, what happens? Each network device, if you dissect them, you get three planes of operations: data, control, and management. So data plane is where the ASICs lie. So ASICs are application-specific ICs that are physical chips which are responsible for carrying the data, right? So when a packet or the frame comes to your switch, these are the circuit who reads the MAC addresses and extracts the payload from it and decides whether to drop it or forward it somewhere else. So that's the forwarding plane. The control plane where all the algorithms lie. So your operating system lies in the control plane. So the routing protocol, switching protocols, they all run here. So think of the control plane runs in the local memory of the network device in the RAM. And the data plane is application specific ICs. So each IC has their own CPU and memory and IO ports. Now, how does this, let's say, network device work? That is that is kind of dictated by an administrator through the management plane. So you tell the router what to do or the switch what to do through the management plane, and this is where the commands come in. And the control plane activates the algorithm and configures algorithm based on those parameters that you have given, and those algorithm will then act on the infrastructure. So this is what a classical network device look like. If you can think of a home router, then your data plane is where your Ethernet cables are connected or your Wi-Fi radio is connected. Control plane is where the actual operating system is running. And when you open the web portal configuring devices, that's the management plane. So if a user A and B communicate, then the data actually flows through the data plane, and there are certain exception that some traffic doesn't need to go to the control plane for processing, because this will then introduce delay. Otherwise, it goes on a straight through data plane. And if you have a large network, then these data planes are connected. So when you have two network devices connected, then you actually connect these data planes. In software-defined networking, what happens? This control plane is now decoupled. Now, decoupling control plane gives you two advantages. First, your control plane or the management plane running on top of the control plane is now becoming vendor neutral. So when you are not caring about what device you are using, then management becomes easier. And there's a local management plane which lets you kind of do some overriding if you want to do in a physical layer. And these two planes are connected over a LAN. Okay. Now, the main difference between the next architecture and this is this communication. I mean, it's not recommended to take place over a WAN network because of certain reason. One is latency. So if we manage, for example, to put this control plane in a cloud, let's say, so something which is not local to your network, then we get into a place called network software defined wide area network, or SD-WAN. So the main difference here is you can see this is not LAN anymore. With WAN, we have a new problem because you are communicating between devices uh, across ISPs. Means there are other network devices lying in the WAN section. So we need to manage those devices as well, right? Now, obviously, people will not give you the right to do management in their devices. So what you can do is to create a kind of private network between the control and the data plane, which will pass through these ISP networks, treating this network as a tunnel. Okay. And also, a new problem appears when you have a scalability issue. Let's say when the user demand increases, you need more scalability. When the user demand drops, you might shrink your infrastructure. So now this infrastructure is not physical anymore. These are all infrastructure as code. So these devices are not physical routers or switches, rather they are like virtual machines running in cloud. So as you can understand, when we introduce more complexity in the system, then managing this whole thing by a single admin is very difficult. So we need a new type of element called an orchestrator. So an orchestrator's job is to orchestrate this management across the control and the data planes. So if you have a large network with different domains and different ISPs, then you need a better thing than going and controlling one control plane only, because you might have a split control plane. You might have multiple controllers running in the network. So this architecture from 8C's standard, 8C is European Telecommunication Standard Institute. Um, from their perspective, this is called MANO architecture, management and orchestration architecture. So it's not just management plane, there's also orchestration plane. Now, what we are getting into is something that doesn't exist in in reality, I would say, because we don't have a device that does this at the moment. But this thing is very much present in research fields and research domains. These are the type of network which we consider as a future network. So when 6G will come, this will be one of those um, elements that would distinguish 5G from 6G. So I'm just going to put a term here, which I haven't put in the slide. It's called self-organized networking. So self-organization is basically a 3GPP concept. So it's there from 3G. Then it was evolved in 4G and in 5G. So in 5G, self-organization has three main pillars. It's called self-configuration, which is what you can see now is automation and programmability of network devices. Self-healing. So it's more of high availability. If one of the device dies, then another device should seamlessly turn on and take control. And then self-optimization. So choosing the most optimal solution should not be explicitly given, but the system must implicitly choose the optimal solution. So what does it mean? That you should have a pool of optimizers, and based on the dynamic condition of your network, the system should choose the most optimal optimizer and then optimize the problem that you're facing, right? So dynamically choosing optimizer stable, then predicting correctly is not a big deal. But the task is to find that hypothesis function which is stable. So in knowledge plane, what happens apart from the orchestration, management, control, and data, this is the place where all the machine learning bits comes into play, right? So all the telecom engineer works in this area where the data plane lies. All the network engineers per se, they work in the control plane side, which involves configurations and stuff. Orchestration is more of a devnet or developer, so DevOps engineer, developer operatives working in the network operations field. And then knowledge plane where the machine learning engineers come into play. Now, problem is nowadays if you want to get into one of this field, you don't need to be proficient in all of them, but you need to know at least a basic of each of these. So knowledge defined networking is a knowledge plane that governs the optimization. So now it's not just numerical optimization, but optimization with machine learning. So how would you interact with such a network, um, a, a knowledge defined network, for example? So this model uh, is kind of, it breaks down that the interaction. So first is intent. From a user's point of view, what you can only express is what you want to achieve. Because as a user, we don't expect you to know how exactly these things are done. So this is what we call an intent. So intent is a context-free sentence. Means when you express your intent, you should not be context sensitive. Means let's say you start you start a TV and you kind of launch an application that can stream 4K video. Now your intent, because you're paying subscription, you want to watch that video, for example, with no buffering. Okay, but you don't need to care about how the network will be provisioned in the back, so that this is guaranteed. Now obviously, if you think about each 4K stream as a unicast stream from the server, that's not happening, because if you kind of multiply the number of watchers times the amount of bandwidth you need for a single watch, that's way above the limit of your ISP, right? So the ISP has to configure their network or communicate with the source server. How is it possible to provide this service to the subscriber without no delay? So that's not your problem. This is the second outcome. Okay, do because the user has an intent. I want to provision that intent. How do I do it? This is what is a task. Intent is more of an end-to-end idea that I am a user. I want my service to be served, and task is to serve that service. Who are the involved entities that in the architecture to do that task? The task is more of context sensitive. So should I configure a router? Should I configure a firewall? Should I do some load balancing here and there? Right. So this is the second phase where the intent gets broken down into tasks, and each task is given to devices which are responsible for giving the service. And finally, these tasks are what? They are basically vendor specific commands. So when you are configuring router, if it's a Cisco router, your command structure will be different. If it's a Juniper switch, that command would be different. So now you can understand the native language for those devices, be physical, be virtual, right? They are actually command structures. And these command structures comes from tasks. The task comes from intent. So this is a new way of doing networking. both in telecommunication network, in service provider network, data center, enterprise. Nowadays, if you want to configure a network, program a network, you don't speak in the network operating systems term. You speak in intent. For example, in 5G architecture, if you see the 5G core architecture, there's a RAN side, the radio area network side, and a core side. And in core, there are multiple functions. And one is called network exposure function, or NEF, that provides you, let's say, network APIs through which you can tell this intent to a 5G network. Okay. And in 5G's term, we call it network slicing. So a slice in network is nothing but a set of quality of service parameters. Let's say to provision that 4K stream, you need certain amount of bandwidth, certain amount of delay. These are the floor and ceiling which are specified for that stream, right? For example, if the content has HDR or let's say Dolby Atmos, then you have additional sound streams coming in. So you need more bandwidth for that to carry those streams. Not only that, they have to be synced together. So there should not be a drift between sound and the video. Therefore, the delay has to be specifically, guaranteed that the inter-arrival delay should not exceed certain limits. So these are called quality of service parameters. And when you specify those in a 5G, core, and it not only configured in one core, but multiple core, which are all involved in that communication, this is called a slice. Means if you think of the total amount of resource that core is given, you are getting a slice out of it, and these slices are reserved for you, um, you know when you are getting that service served. So I think this is kind of now clear that what is intent and what is task and what is command, because these three layers are very, I would say, crucial to be understood. Otherwise, um, while referring to the following slides, it would be a bit messy. Right. So how exactly this math happens? There are really three. So now we're talking about the state diagram of processing the intent and task and commands. So let's think of like the three sets of, there are three domains are there. One is intent domain, one is task domain, and one is command domain. So command domain are obviously they are device specific, and the task domain, which is more of a unit amount of task. An intent that doesn't care about all this, it's just an intent. It just wants something to be done. So an intent, when it is called, it's an invocation procedure, and the intent actually launch a task. Now this task, the first one is the starting one, is the entry point of the task set, and then it might go through multiple tasks. So for example, here you can see that two intents are processed and invoked, and the intent one calls T1, and then T1 hands it over to T2 and then to T3. And I2 invokes T2 and then T3 and then there should be T4 actually, this one. So this is a simple call graph. And now if you think about the DevOps side, these tasks are nothing but containers, okay? And these containers are exposing some APIs. So for example, I1 is doing a get request to T1, and T1 is processing something and then posting that to T2. So once these things are done, what is actually happening inside, this task is calling commands. Now, when you finish the entire call graph, you eventually get another a context diagram, for example, for commands only. And these commands are then translated into scripts, and these scripts then are sent to the devices. So what I just defined in the last slide, task versus intent versus commands. If you want to kind of build such a prototype, this is your model. You are actually mapping between three domains. One is the intent, the task, and the command. And then to implement it, you use mainly DevOps principle like containerization with Dockers, and then orchestrate them with things like Kubernetes. So this is sort of a boilerplate if you want to build such a system. Finally, um, what type of service that we are aiming to to run in such a network? So one is routing as a service. This is a domain that I've been working for last couple of years. Um, so routing, as you know, is a process that eventually finds the shortest path between the source and the destination. So also this problem, I rather say pathfinding, not routing. Routing actually means that, let's say, if you want to go somewhere and you don't know the best exit path for it from your side, so you rely on your neighbor's information. If they know where, how to reach there, if they don't know, they would rely on their neighbors. And this recursive process is called routing. That you are basically asking your neighbors, hey, do you know how to get there? If they don't know, they will ask their neighbors. And traditionally, there are two major types of routing that exist. One is called interior gateway routing, that happens inside an enterprise or a same administrative domain. Means all the network devices are on the same administrative control. The other type is called exterior gateway routing, which happens between administrative domains. Okay, so think of domestic flights as interior gateway routing and international flights as exterior gateway routing. Now, for the exterior gateway routing, the protocol is kind of universal, is BGP, and border gateway protocol, and sometimes called BGP is the protocol of the internet, because internet is nothing but network of ISPs. The problem with IGP is there are two ways this this neighborship is formed. One is called distance vector, where we also call it routing by rumor. Means you get the idea from your neighbor how to get there, but you don't have a way to verify how did your neighbor get it from. So the chance of creating a routing loop, maybe you rely on somebody who relies on you indirectly. So that's a routing loop, and it's a problem always exists in distance vector routing. In link state routing, the other side is called routing by propaganda. Means you get information from your neighbor, and you don't do any change. You simply flood it to your neighbors. So you don't do any local optimization. So both has issues. For example, distance vector routing is more space efficient because it doesn't store all the routes. It does local optimization, so it actually introduces a bit of processing load to the devices. The problem is it has this issue of routing loops, which doesn't exist in link state routing. But in link state routing, the problem is that the storage complexity is very high, and therefore routing protocols, for example, OSPF, they split this routing table into other defined routers and group them into areas. And surprisingly, between the areas, they do distance vector routing. So pure link set routing is a myth. There is no pure link set routing. There's always link set routing within the area of the domain. Now, why did I give you this introduction? Because um, there are always problems in network optimization. That okay, I like link set routing, but I like some properties of distance vector. For example, I like OSPF's way of storing or do the hierarchical routing in a large network. But the metric that OSPF uses is not that good. It's just bandwidth. What if I want to do my metric calculation on delay, on reliability, on load? I can't do it. So there was a demand from long time that is it possible to make routing not a layer 3 problem that happens in the router, but a layer 7 problem that happens in the application layer. Technically speaking, BGP is a layer 7 protocol. It's not a routing protocol that runs in the router natively, because it runs in above TCP, so it is not a layer 3 protocol. However, BGP has a special way of working, and it's a very slow protocol. For example, if a route maps in your network, then it takes around 30 seconds. Okay. So, is it not good to have a way to define your own routing protocol without changing anything to the network? This is exactly what routing as a service means. So, this as a service is a more of like cloud centric terminology, like software as a service, infrastructure as a service, platform as a service. So when we say as a service, it means something that is pre-compiled and kept into cloud, and whenever you need it, you get an option and use a service. So what routing as a service provides you is, I'll not get into details of this diagram like step by step, but if you want more about it, ask me in the Q&A section. The whole idea is there should be a way that the administrator can speak to a global control plane, defining the metric, define the routing logic. So I can define my own pathfinding algorithm. I can define my own cost function, and then give it to the RAS or routing as a service server, and this will compute the path and then communicate with the respective controller in the control plane, and then the controllers will translate those into device specific commands and then speak to the network devices. Now this could be a software defined network, for example, a network that is operating on open flow protocol, which is more of like SDN kind of protocol, or a classic network where it might run on SSH or netconf or sconf. So if you don't have an intent based networking platform, this is just a picture to be stared in a research paper only. You cannot implement it because you don't have a platform to implement it, and no vendor will give you the authority to go and change the network in this way if you don't have a stable medium in the middle. So this is one example. The other one, as I mentioned, is machine learning as a service, and this is kind of getting a lot of traction nowadays. Is creating machine learning models, training them, and optimizing certain problem with those models as per demand. So it's an intent-based machine learning kind of problem that uh, I have a problem to solve, and I can understand that if I know the trends or the hypothesis from the data set I collected, I could solve it better. The problem is, let's say I'm not a machine learning engineer. I don't know how to code machine learning, models in TensorFlow or in PyTorch. How can I use existing model to solve my problem? So here you can see the idea is the client would send an intent, and the intent would carry a data set and metadata, which is more of like hyperparameters and parameters, and then they will communicate with something called API agent, through which they communicate with the backend, and the backend has a set of model builders: machine learning, deep learning, reinforcement learning, federated learning. And based on the data set and based on the type of model you have chosen, let's say you define, I need a deep neural network of X number of neurons in Y number of layers, and then each layer contains a Z number of neurons, and then the optimizer is such, the loss function is such, and here's my data set, a number of epochs maybe such. So with all this information, you give it to the model gets trained with the data set and gives you back a trained model, right? And not only that, it also caches that model, because RESTful API also, one of the principle of REST is cacheability, that you not only create that model, but you cache it somewhere. So if next time a similar data set comes and the distribution of the data set matches with a known distribution, then you don't need to go and kind of train the model from scratch. You can do like ensemble learning or similar stuff where you can just update an existing model and send it back. On that regard, um, I'm not sure if you're familiar with this term, federated learning, which is now getting a huge traction, especially. I mean, obviously, we've been using this backend for a long time, maybe without knowing. Uh, a good example is Grammarly, let's say. So when you type a word and you correct it, um, how does the Grammarly server know that what would be the next expected word that you're going to type based on a previous typed word, and how you're going to inform you based on someone else's corrections. So this whole process is a closed loop design, means individual device do a local learning, and this learned model is shared in a way that the actual data is not reversible from that model. So it just takes that data privacy term, and then it kind of gets those model from each of the clients and averages it and creates a global model and sends it back. Now this is how what happens. The central server gets a idea about the behavior of the clients. Now just replace those clients from mobile phones to network devices. Now not only you can get network statistics as you are getting from any other protocol like SNMP, but you're getting the different kind of flows. What type of network flows are happening there? What type of protocols are going through that router? And through this, the network eventually understands which type of traffic is more suitable for this network. So now with that idea, you can steer traffic between different devices and optimize the network in a way that devices which are suitable for certain amount of traffic will be given that type of traffic only. Okay. So a simple example how this thing works, and it's a bit mathematically explained here, and I put my paper on the corner that where this whole thing is described. So think of a network of certain amount of routers, and think of each of the link has an optimizer given, that carries a minimizing objective function with some free variables and a set of constraints. So this superscript E stands for edge, and the superscript N stands for node. So if we know certain statistics collected in the node and the edge side, then this whole problem becomes a set of optimizers, which requires parallel optimization, and they're all constraint optimization. Now, if we give this to a machine learning agent, the approach that they're going to use is, all right, so you optimize it for a given timestamp, and we keep monitoring how the the x the k's, for example, or the x's are changing over time, and based on that, how my optimal result is changing over time. Now, if I can make a track of this, then what I eventually get is a set of time series, and with those time series, if I train, let's say, a recurrent neural network, right, which is actually there for solving time series problems, then we have a hypothesis which can predict what's going to happen in the future. So let's say you see one of these routers is behaving, abnormally. There's a delay suddenly increasing. The certain problems are there. There's certain spikes in the performance. Then it might not be selected in the next phase where a huge amount of traffic comes, because now this can be a single point of failure. Okay. So cognitive routing is a domain of routing which specifically uses machine learning principles to solve routing problems. So if you remember, I mentioned these four pillars of 6G, the self-organized networking pillars: self-optimization, self-configuration, self-healing, and self-learning. Now, if you can put those four principles here, your optimization problem here is routing. So what you're trying to optimize is the find the best possible path among multiple paths. Um, Self configuration means I need a way to somehow configure these routers to follow the path calculated. Self healing: if one of the router dies, then the other router should take control and steer traffic immediately. And finally, self learning means managing a time series in this case, to learn the behavior of the network. Okay. And please understand, this is not always physical routers. There could be logical routers as well. You can create a whole network infrastructure in AWS or GCP, in a cloud platform, and these routers will be virtual machines. So the problem with virtual machines are, if your host machine gets too busy, or one of your VM makes your host too busy, then it steals cycles from other VMs, and you will experience a problem that without doing anything in any VM, these VMs are getting used for 30-40%, but you're doing nothing. So where this 30% is getting used from? Because some other VM in your network is kind of stealing your cycles to do their jobs. There are ways to kind of fix it, but this is a common issues in virtual machines and virtual networking. So it's not that obvious in physical devices because they have their own physical resources, but in virtual devices there is an issue. So obviously knowing these statistics can prevent you to have any failures or any timeout problems, because nowadays if you, let's say, graduate from the university, you get a job in a product based company, you'll be working on a product that kind of signs an SLA of let's say a 5.9 reliability. Means you're looking at 99.999% of reliability. Some products like cloud operating systems, they provide 7.9 reliability, which means that you can only afford to turn off your service around like more than a minute for a year. So you can understand that you need some automation implemented in your infrastructure that would kind of detect problem and solve problem in real time. And for that, you need a network between that allows you to communicate between devices. So quickly, if I go through it, what happens here that each node cost, the Cn of the ith router, comes from a function Fn, and the link cost is Ce between I and j. Now, if you have Cn and Ce, then the Cn behaves like a self loop in the router. If you think this as a graph, and if you have a self loop here, a weighted self loop, then it's not a simple graph. And if it's not a simple graph, you cannot do um, any shortest path on top of it because that's a prerequisite. So one of the idea is that I did in my previous papers is to normalize this cost into the edge cost, and I named it STEN as stochastic temporal edge normalization. It's a technique that I kind of put to solve this problem. And then you don't have a node cost, but this cost gets normalized in the edge, and the edge cost changes over time. And you see all these t factors, the time factors, because now we are talking about a time series. And then you get a tree-like structure from it, which kind of tells you all possible ways two nodes can be connected. So it's a typical dynamic programming problem. So I want to connect R1 and R2. So all possible ways R2 can be connected to R1. And if I now follow memoization or tabularization or even cutoff here, I can control the depth of the tree and I can control the computational load. So from the network, first normalization and finding all possible ways, and then this can be stored in my controller. So this tree could be my representation of routing table. So if I want to go, let's say R1 to R2, and I find okay, there's a direct path, but if that R1 R2 path is dead, then I don't have to go and reroute it. I know the other option is through R6. If this path is also dead, I have another option through R3 and R4 and then R6. So you see, if you have these things pre-computed, which is more proactive computation, then it is very easy to do self-healing, and it will happen almost real time. Question might be there that why then don't we have this in the real, today's network? Well, there is a way of doing this, and this is exactly what link set routing is. But the problem is, if you do this, first of all, your routing table will be huge, so your network will exhaust the memory. Sorry, your router will exhaust the memory very, very quickly. Secondly, um, to build this table, you are talking about exchanging control information between physical devices, and that will also load the network, and that will also occupy your control plane of your network. So 50% of your bandwidth will be only wasted by exchanging packets. In this case, we don't have that issue because the controller runs this whole calculation in its local memory. So it's not physical devices which are communicating packets. That process is in your in the server exchanging information. So it's much more faster. So yes, computationally it is a NP hard problem, sorry, NP complete problem. But if you control, for example, let's say the depth of the tree, or um, do some dynamic problem optimization, let's say memoization or tabulation, these things can be optimized. And finally, this graph then gets encoded into a state diagram, and this state diagram becomes my actual matrix representation of the control table, routing table. So with that, um, finally I have a architecture to actually present where all these layers comes together, where the knowledge plane is, where application control data plane is. And this is a actual test bed representation. So if you go to this paper, I have explained that if you want to build such a test bed, what exact technologies you need to connect, and to provide these services. um, so I think that's from my side. I don't know how long I had taken, but yes, if you have any questions, I'm happy to answer.
Thank you, sir, for the wonderful session. Now I would like to hand over the session to the session chair, SK Abdul Rahim sir, HOD CSE. So, sir, please.
Many thanks to Dr. Saptarshi Ghosh. In spite of having busy schedule, Dr. Ghosh has given a nice session, has presented a nice session. It's really very innovative, and I think the participants will be very much benefited by attending this type of workshop, seminars, especially in this domain, machine learning and data science, deep learning. I think our students will be very much benefited. So next time, whenever we will try to organize any FDP or any this type of programs, definitely I will request Dr. Santanu Madhu sir to contact with Dr. Saptarshi Ghosh sir, so that later on also we can utilize his knowledge, his ideas with our students. So now our participants have some questions regarding the session. So, sir, I am telling some questions one by one. You please give the answer so that our students will be benefited.
Sure.
So, one question is that for what kind of data set will federated learning work better than the other types of machine learning algorithms?
Right. So as I mentioned, if you're using data sets are um, for federated learning is not a different type of data set you're looking at. What you're looking at is the distribution of data. So the study of federated learning came from the fact that how can I distribute data to a third party which will learn from the data without seeing the data. So the first principle is the data has to be sparsed and distributed. So the data source should not be centralized, right? So let's say whatever content you watch in your phone, that's a local data set that is kept on your phone, but you don't share that one. So you share a trained model, right? Similarly, there are other hundreds of users using their phones and their applications, and their local model is getting trained in their phones. Now your averaging function, which runs in the central location, it takes all this trained model and averages it and creates a global model and sends you back. So to precisely answer your question, the first principle is you must have a sparse data set, which is distributed among multiple devices, and expecting they're coming from different distributions. Okay, because if the distribution is known, there's no point of having distributed data sets, right? Given that when you average them, here we use normal distribution. So when you average them, then this distribution should not exceed a certain threshold of loss from the model that was trained on your local devices. So first, distributed and sparsed, and secondly, it's a closed loop learning. It's not just you give data and train a model and get a trained model back. It's a continuous process, which you can also refer to reinforcement learning type of models. It's a closed loop.
Thank you, sir. Another small question is there. What is network slicing?
So network slicing, I'll first give us a simple definition, then I explain it. So network slicing is if you have a network infrastructure with multiple MNOs or mobile network operators, then each operator has their own resources, right? Um, Own network devices, telecommunication infrastructures, and stuff. So network slice is a virtual allocation of resources across multiple MNOs that guarantees certain services. For example, if I want a service that requires certain amount of bandwidth, certain amount of delay, I don't want, let's say, latency more than 10 milliseconds. So a slice is a logical way of telling all the devices between me and the server that, okay, give priority to this traffic in a way that the latency should not exceed the guaranteed one. Okay, so it's a logical share of resources across multiple telecommunication operators.
Okay, sir. Thank you so much. Another two questions are left. Uh, what is self-aware cognitive radio?
Right. So cognitive radio is not my domain of research. Yeah, this is more of um, a radio or a telecommunication engineer's domain. That's why I initially mentioned that I'm not a radio person. Um, there is something called software-defined radio, which means you can tune the reception and transmission bands through software APIs. Cognitive radio is something that also gets tuned by some learning function. So whatever you are doing on your radio stuff, you're collecting data out of it, and you are running some machine learning algorithm to learn, let's say, classification or regression kind of task, and feeding it back to the radio. One quick example I can give you is let's say noise detection. So your radio is there to receive signals, and there are noises, and there are sometimes jammers which try to jam that spectrum. So a simple classification algorithm can be applied, which can see the noise floor and try to find out a center frequency in your spectrum, such that the noise floor is always below certain level. Right. So this is an example of cognitive radio, which uses machine learning principles like classification principles to program a radio through software.
Thank you so much, sir, for giving your valuable time. It's really very appreciable, and students are they will be very much benefited. Thank you so much, sir.
My pleasure.
Dr. Santanu Modik, sir. Anything else? Modik, sir.